All right, let's talk a little bit of gas law stuff. The equations and how to use those equations to solve problems. There are four primary or basic gas laws that we talk about. There's Boyle's, Charles, Gay-Lussac's, and Avogadro's. Each of these gas laws take two of our four variables for gases and relates them to each other. The four variables are pressure, volume, temperature, and amount. Pressure is measured in units like atmospheres or pounds over square inches or newtons over meters squared. Volume is measured in liters or milliliters. Temperature in Kelvin. We use the Kelvin scale for these because of its lack of negative numbers. And the amount will be measured in moles. Boyle's law looks at the relationship between pressure and volume. And this is pressure and volume are inversely proportional, provided that temperature and amount remain constant. Mathematically speaking, it ends up providing an equation that looks like this. P1 times V1 equals P2 times V2. If we want to maintain the equivalence and increase the pressure, we would have to decrease the volume to maintain our equivalence. When one goes up, the other one goes down. That is an inversely proportional relationship. Charles' law is all about the temperature and volume. Again, if the temperature and volume are the relationship that we're going to look at, the other two variables, pressure and amount, have to be constant. And it says, if pressure and amount are constant, temperature and volume are directly proportional. Mathematically, that works out to be V1 over T1 equals V2 over T2. Again, it's an equivalence we're trying to maintain. If the volume goes up, the temperature would also have to go up in order to maintain that equivalence. If a temperature went down, the volume would also have to go down to, again, maintain that equivalence. They change in the same way, and because they change in the same way, that is directly proportional. Gay-Lussac's law is similar to Charles' law. We're going to see what temperature does, but this time we're going to see what temperature does to pressure. And again, the other two variables have to be constant. So it says, if the volume and amount are constant, temperature and pressure are directly proportional. Charles' law was directly proportional. Gay-Lussac's law is directly proportional, so their equations look very similar. P1 over T1 equals P2 over T2. Again, what it means is if we're going to increase a pressure as we move across the equal sign, we're going to have to increase the temperature along with it to maintain the equivalence. When one goes up, the other goes up. If we're going to drop this pressure across our equal sign, we're going to have to drop that temperature across the equal sign, again, to maintain the equivalence. Directly proportional. They both change in the same way. Avogadro's, again, similar to Charles' law. But instead of seeing how the temperature affects volume, we're going to look to see how amount affects volume, N and V. And as always, the other two variables have to be constant. So pressure and temperature must be constant. And if they are, amount and volume are directly proportional. Again, another directly proportional law means that we're going to see a very similar equation. These are the directly proportional laws. And again, because they're all directly proportional, we see very similar equations in those three. Boyle's is the only inversely one. So it looks different. Now, mathematically, we're going to approach them all the same way. Because in the end, because of the potential for variables in the denominator, we're going to end up cross-multiplying whenever we do problems with Charles' law, Gay-Lussac's law, and Avogadro's law. And that cross-multiplying will make the equation look like Boyle's law. So mathematically speaking, when it comes time to do the algebra, when it comes time to solve for one of those variables, all the math is the same. We do, however, have 4 equations to work with. So we're going to have to be very careful to identify our numbers, figure out what they are. We have 1s and 2s, initials and finals for all of these. 1 means your starting value, 2 means your final value. We're going to have to identify those things correctly in order to put them in the right spots in the equations in the first place. But once we have that done, once we have our equations set up, the math is very straightforward. These are some of the practice problems that I gave you to do for homework, for practice on this stuff. And this is from the mixed set of math problems. So it doesn't tell us what law we're working with. We have to figure that stuff out for ourselves. And again, to do that, we have to look at what these numbers are, what these numbers measure. We have 5.0 liters. We have 300 Kelvin. We have 270 Kelvin. Well, we know liters measure volume. And we know Kelvin measures temperature. We have 2 T's and a V. We must be missing another V. These are T's and V's. Temperatures and volumes are Charles' law. So we know it's V1 over T1 equals V2 over T2. These are the ingredients we have. This is the equation they fit. Now we do have to figure out the 1s and 2s, and for that we have to look at some textual concepts here. We have from and to. Those are 2 of the big words I told you to look for. From indicates where you're starting, to indicates where you're going. So we're going from 300 Kelvin, that makes it T1, to 270 Kelvin, making that T2. These numbers are interrelated. The gas has a volume of 5 liters. It's heated from this to this. It implies that this is V1 or given, and we're looking for V2. It does over here confirm that by saying new volume. Again, when you're dealing with something like the pressure law, it's not really important to read the question all that carefully. You can look at the units. You can figure out what's P, what's F, what's A, and put them in where they belong, solve it. But since these equations have 2 V's, 2 T's, 2 P's, 2 N's, you have to figure out the initial final stuff, which means you actually have to read the question. It's in the context of the question you'll figure out what your initials and finals are. Once you've got that, you can substitute 5.0 liters over 300 Kelvin equals V2, our unknown, over 270 Kelvin. Now the best way to approach these problems is just to cross-multiply, get rid of all that division right from the very get-go. This will be very helpful in making all the math consistent. It'll also be necessary when your variable's in the denominator. You've got to move it out. So why chance it? Just go ahead and cross-multiply it all the time. You'll never worry about missing one of those variable in the denominator things. You'll make it all look like Boyle's law, and they all will solve the same way. So we have 5.0 liters times 270 Kelvin equals 300 Kelvin times V2. Simplify the side we've got. We can simplify this side of the equation by multiplying 5.0 times 270. That's 1,350. And it would be liters times Kelvin, because that's what we did. We multiplied. We haven't done anything to this side of the equation yet, so it's still 300 K times V2. Now we can solve for V2. We can isolate our variable. We're multiplying by 300 Kelvin, so we'll divide by 300 Kelvin to isolate it. What you do to one side, you have to do to both. legible. Over here, that cancels out the 300 Kelvin completely and leaves us with V2. Over here, it cancels out the Kelvin, leaving us with the unit liters. We'll do 1,350 divided by 300, and we end up with 4.5. Now, important, we can go back and self-check this. This is Charles' law. Charles' law tells us that volume and temperature are directly proportional. What you do to one, you have to do to the other. We look at what's happening to our temperatures here. Our temperature is going down from one side to the next. So we would expect our volume to also go down. And we went from 5 liters to 4.5 liters. It did indeed go down. That gives us a good idea that we've done this correctly. If we had gone back and checked that and we saw that the volume went up, we know we did something wrong. We may have mislabeled something. We may have done our math wrong. It tells us we have to go back and check our work again. Take a look at the next one. Again, 3 numbers. That's what I'm going to give you. We have 5.0 liters. We have 2.5 liters. And we have 3 atmospheres. Liters measure volume. Atmospheres measure pressure. We're missing a pressure, so we know we're trying to find one. We have to figure out what's what. And again, that involves going back and looking for context clues. Initial pressure is 3 atmospheres. That means this is P1. New pressure we're trying to find. We're trying to find P2. Compressed to 2.5 liters. That means 2.5 liters is our final. We must have started at 5.0. So again, it's all context clues that tells us which one are the ones and which ones are the twos. So you do have to read these questions carefully. This is Boyle's law. It's the only one with P's and V's. P1 times V1 equals P2 times V2. Again, this dictates what equation we have to use. You pick the equation that matches your variables. This is Boyle's law this time. P1 is 3 atmospheres. V1 is 5.0 liters. Don't ask me why I use time signs at the top and now I'm using brackets this time. It's been a long day. P2 is our variable. V2 is 2.5 liters. Again, let's simplify the side that is complete first. So 3 times 5.0 is 15. We're not using significant figures, so don't worry about it. 3 times 5 is 15. It's atmospheres times liters because that's what we did. Over here we haven't done anything, so it's P2 times 2.5. Now we can divide both sides by 2.5. Isolate our variable. We're multiplying by 2.5, so we do the opposite to isolate. Over here, the whole 2.5 liters cancels out, leaving us with P2. On the other side, this is liters. Liters cancel. So atmosphere is the unit, as we would expect with the pressure. 15 divided by 2.5. 6 atmospheres. And again, we can use the relationship that's in the law itself to figure out if we've done this correctly. Boyle's law tells us the pressure and volume are inversely proportional. When one goes up, the other one goes down. So let's take a look at our volumes. From V1 to V2, we went down. So we should expect our pressure to go up. We went from 3 to 6. It did go up. It went up by the same amount. We basically cut this in half. 5 divided by 2 is 2.5. So we'd expect to do the opposite to the pressure. It should double, and it did, from 3 to 6 atmospheres. Take a look at number 9. We have 4 liters. We have 2.5 moles. And we have 0.25 moles. Liters are a volume. Moles are an amount. I didn't spell out the word moles. That's not meters, that's moles. We're missing a volume, so we're trying to find a V. Again, we got to figure out which one's the initial, which one is the final. Decreased to 0.25 means that's our final. Or 0.25, I'm sorry. Not 2.5. Decreased to 0.25, so that's our final. The 2.5 moles was where we started. The way this is written, these two numbers are linked together. So since this is a 1, that must also be a 1. It does even tell us here we need to find the new volume, so we're trying to find the final. Avogadro's law is what that is. V's and N's, that's the only place you find it. V1 over N1 equals V2 over N2. So 4 liters over 2.5 moles equals V2, our unknown, over 0.25 moles. Again, the way we want to do this is cross-multiplying. We don't have a variable in the denominator this time, but we could. And when we do, we have to cross-multiply anyway. So you might as well just do it all the time. That way you don't have to worry about missing one. Again, it'll make it look just like Boyle's law. We're solving all these problems the same way. We don't have to worry quite as much about what we're going to do. So 4 liters times 0.25 moles equals 2.5 moles times V2. Again, because we've done this, we do them all the same way. We simplify the one side, the side that's complete, the side that has the 2 numbers on it. We multiply them. And then we divide by the number on the other side. As long as we cross-multiply, then everything ends up working out the same way. 4 times 0.25 is 1. Liters times moles. We haven't done anything to the right side, so it just stays the way it was. Now we have to isolate and solve for V2. Because we're multiplying by 2.5, we will divide by 2.5 to isolate our variable. What we do to one side, we have to do the other. Over here, we're left with nothing but V2. Over here, the moles cancel out, and we're left with liters. It's 1 divided by 2.5, which is 0.4. Now, again, we can use the relationship to make sure we did it right. Avogadro's law is one of the directly proportional laws, so you change them in the same way. Our amount went down, so we expect our volume to go down, and it did, from 4 liters to 0.4. Specifically, we took this amount and we basically divided it by 10. So we'd expect to take our volume and divide it by 10, and that's what we did. If the amount got 10 times smaller, then the volume has to get 10 times smaller as well. Well, that's all I'm going to work out. The rest of them you have to work out. You need to be able to do this for our quiz tomorrow. I am going to put the answer key up here so that you can check your work. I didn't do all of this. I didn't do all this listing out of stuff, show all my work, etc. It's just basically an outline of what the equation looks like in its substituted state. And then I use that to find the answer. So again, when you look at what I did here, I just kind of laid out the equation, put everything where it belonged, and then in my head did the math. These first 2 are Boyle's law because we have pressures and volumes. Number 3 on here is, again, Boyle's law because we have pressure and volume. Milliliters this time instead of liters. Number 4, we have pressure and we have temperature. Pressure and temperature is Gay-Lussac's law. We have pressure and temperature again on number 4, or number 5. Sorry about that. So again, another Gay-Lussac's law. On number 5, Pressure and temperature again, Gay-Lussac's law. I think I already said that. Again, it's been a long day. Number 6 is volume and temperature. Volume and temperature would be Charles' law. And then the rest of the ones on the second side of this, the ones that I did not calculate, numbers 10, 11, and 12. Number 10 is another Avogadro's law, amount, moles, and volume. Number 11 is volume and temperature, that's Charles' law. And number 12 is pressure and temperature, so another Gay-Lussac's law problem. Again, when I grade your work on this, I look at your answers and I look to see if they're right or not. I'll look to see if you have the right number and the right unit. Round where you want to round. We're not doing significant figures. I'll know what you did. But if you got the right answer and the right unit, that's all I care about. I don't look at anything else. I don't look at the rest of your work. So if you wanted to do it the same way I did it, just writing down a skeleton, it's kind of easy to figure out how to solve this. If I have this written down, I know I'm going to multiply these two numbers, so I do 300 times 3, and I know I'm going to divide by that one, and I divide by 1. I mean, you can do that too, and I'm sure a lot of you are good enough at math that you can do that too. No issue. But if you're in doubt, write it all out. If you're in doubt, show me all the work. Give me everything so I can see if you made a mistake, where you made a mistake. I can see, did you make your mistake in labeling the 1s and 2s? Did you make your mistake in what you substituted? Did you use the wrong equation? Was it just a math error somewhere? Everything's set up right, but you just made a mistake here at the end. Maybe you did 2.5 divided by 1 instead of 1 divided by 2.5. I don't know. If that's the case, I can give you some partial credit anyways for getting things labeled correctly and the equations set up correctly and all that. I'll just take off points because you can't divide. But again, there's no partial credit if there is no work. So you got to make sure you give me something to look at.